Please put your hands together for the most badass newsreaders of all time.
Hello and welcome to a special edition of S.T.A.T.S. News. Coming up on tonight's show, we take you into the magical world of statistical hypothesis testing. It's going to be thought-provoking, it's going to be challenging, but most importantly, it's going to be awesome. Hell yeah. Coming up first on tonight's show, we have a young Imperial graduate. He studied a degree in civil engineering and then went on to do a PhD in statistical hypotheses. He's certainly one of the best math teachers I've ever seen. He's probably best well known for his Rose theorem. So, without further ado, let's hand over to Professor Stephen Rose. Hello there, children. I'd like to take a moment to talk to you about the fabulous world of statistical hypothesis testing. I have a pen ready. Let's begin. Oh, sorry about that. I was just going through some theories before we started filming this, so let's just get rid of those a second. Okay, so you're probably sat there wondering, what is a statistical hypothesis testing? Well, first of all, let's learn how to spell it. H-Y-P-O-T-H-E-S-I-S, hypothesis. Now, basically, it's an assumption for a parameter that we don't know. So, say we don't know the mean of something. We can make a hypothesis for what it might be. We call this initial hypothesis the null hypothesis. It's represented by H0. So in our case, we could say that the mean, mu, is 5. But there would be some other radical people who might take a different view. They might take the alternative hypothesis. They might say, whoa, hold on a minute there, Steve. Mu probably isn't 5. It's probably much bigger. So they would say that mu is greater than 5, completely contradicting what I just said. So now, how can we test this? These radical people need some kind of way to prove if they're right or not. Well, if we look at our normal distribution, you can see that all the data is distributed in this way, the characteristic shape of a bell curve. Now, the H0 region basically represents all of the data that's close to, in our case, 5. So if this is 5 here, we can say, if we take a random sample of these things, measure all the means of them, if we get something pretty close to 5, then we can say, yeah, Steve's a stand-up guy, he's probably right, like always. But basically, these other people think that it's greater than 5, so if it's getting quite a lot greater than 5, they might think, hang on, Steve's probably wrong. Actually a lot bigger than 5. We can call this little region here of the values our critical region. That's the one that proves, I've written H0 twice, excuse me, that's H1, which proves H1 to be true. And this exact little point here is the critical value, CV, if you will. But hold on a minute. This is a one-tailed test. There's also something else you need to know for your exam. That's a two-tailed test, baby. Basically, instead of a H1, we could have had a H1 that mu is just unequal to 5. That's for these crazy people who can't make up their mind which way they want to go. They're just saying, you're wrong, but I haven't got a clue which way it's going to go. And that would look something like this, where the critical values and the critical regions are now on both sides of the normal distribution. So that's the mean, if you like, and these are both critical values. Now, an important thing to note is that every test has an associated significance level with it. We could say here, I don't know, let's go for a significance level of 10%. Now, in the first case, that would mean that this area here represents 10% of all the area covered by the normal distribution curve. But when we come down to this bad boy here, this two-tailed test, then each side has to represent 5%. So this is 5% here, and this is also, you got it, 5%. And there we are. So that's a quick glimpse at statistical hypothesis testing. We'll be right back for more shortly. Thank you very much. Back to you, Paul.
Thanks, Steve. That was mind-blowing. Now we're going to go out and we're going to see what the public make of this new craze, hypothesis testing. Over to you.
So we decided we'd go out onto the streets and see what the public thought about hypothesis testing. So, you see, yeah. Hypothesis testing, what do you think about this new craze?
What?
This new craze, null hypothesis testing, alternative hypothesis testing, what do you think of it?
Like, what do you think? I've never heard of it.
Never heard of it?
No.
Oh, come on, you must have seen Professor Steve's program. It's awesome. Yeah? Professor Steve?
Never heard of
Rose
Texas
theorem, do you know Rose theorem?
Nah.
Never heard of Rose theorem. Ooh, cool. Right. Yeah, well, yeah, hypothesis testing is a bit of a statistics phenomenon at the moment. We're happy to be connected. What do you think? What do you think?
I'm going away. Yeah, you're scaring us now.
As you can see, the public love hypothesis testing. It's all the craze these days. Thanks. Back to you.
Moving swiftly on, we're now going to take a quick commercial break. Stay tuned. We'll be back soon with more S.T.A.T.S. news. Calm down there, little buddy. Are you suffering from the calculator blues? Or maybe you just got to A-level maths and realized it's not just numbers. I'll tell you what you need. You need the Capio FX991ES Plus. It's the new calculator.
But I thought maths was just about adding numbers.
Oh no, Paul. I'm afraid you're terribly wrong. You see right here? Integral. Yeah. You see right here? Differential. You see right here? Matrix mode. This baby's got everything.
And I've heard of this angles in radians. What is that?
Oh, this is a whole new world. You see this? Sine function. You see this? Right here? Change. Degrees or radians. Take your pick.
That's amazing. My maths fearing days are over. Thank you, Steve.
Don't thank me. Thank the Casio FX991ES Plus. Available in all good stores now. Hurry while stocks last.
So, are your A-levels giving you trouble? Do you want to get into a university where you just don't even have to work? Well, maybe the University of Scunthorpe's for you. I'm sure you've heard recently about the hiring of the university fees. Well, I'll tell you something. Here, at the University of Scunthorpe, we are lowering those fees, alright? We don't need your money, because, you know, our courses, they don't need money to run. We just, you know, we're here for you. I mean, we've got great facilities. I mean, we've got a bar for drinking, and yeah. So as you can see, this is our main campus building. It's quite a sight. I think you'll agree. Quite a sight. Well, here at the University of Scunthorpe, on the leaderboards, I'm sure you've seen the leaderboards. I mean, we are the #1 for the university in the whole of the UK. The #1 university, okay? I mean, you know, everyone knows our name. Everyone knows us. You know, we're famous. Here at the University of Scunthorpe, we've even got degrees, not even offered by the likes of Oxford and Cambridge. Degrees like how to break this bike lock. I mean, who doesn't want this bike? I mean, look, it's worth a pretty penny. I mean, stuff like hiding from the police and joyriding. Joyriding is quite a good one. The art of driving while you're drunk. It's a very a full course, and it helps you to live in this 21st century. So yeah, the University of Scunthorpe. the best place to live.
Welcome back to S.T.A.T.S. News. Steve. Steve. Okay. Right, we're going to go back to Professor Rose as he delves deeper into the understandings of statistical hypothesis testing. It's sure to be a good one. Let's take a look what happened.
So, welcome back to another exciting episode of Professor Stephen Rose Teaches Statistical Hypothesis. Now, last time I went through a few basic concepts. I taught you basically what is statistical hypothesis testing. But now you're probably sat there thinking, why would I ever use this? Well, what's this useful for? How can I apply this to the real world? Well, I'll tell you. You see, I was flicking through New Scientist the other day, and they said that the population of a rare species of anaconda, the length of these snakes basically is normally distributed with a mean 10 and, to quote, a standard deviation of 2. So I've set out on a quest to test this, really. Let's start out by saying what they said in the book. So they basically said that X is distributed normally with a mean of 10 meters. This is, they're pretty huge snakes, and a standard deviation of 2. But when you're writing out the normal distribution, of course, this parameter is the variance, which is the standard deviation squared. So let's go and whack a 2 squared onto that. So let's identify the null and alternative tests for this testing. H0, what they said in the book, is that the mean is 10. But I'm inclined to believe that it's not 10, really. They're probably wrong, like usual. Awful magazine. So I'm going to say that mu is unequal to 10. Now, you could probably represent this on a normal distribution curve once again. So let's have a look at our bell curve for this. Not in that way. I'm going to pick about a 2% significance level for that, which means that my critical regions, either side, are going to have 1% of the area of this whole curve each. So that's 1% over here, and another 1% over here, making a total of 2%. So yeah, the next thing that we need is some real data. So don't worry about catching any of these snakes. I did it earlier. I went out and I caught a whole 25 of these anacondas just for this demonstration. And I measured the length of all these great beasts. And you know what I found? I took the mean average, my favourite kind of average, of all their lengths. And I actually got my mean, I'll call it mu Steve, of 11 meters. Shocking, I know. So now, we have to take, you see, this is the population distribution, but I want to find out what the distribution is just for the sample that I've collected. So, like I said, I collected 25 snakes. The mean we would expect to be the same, so you can say that X bar is distributed normally with a mean 10, and the standard deviation now, we have to do the variance divided by the sample size. So the variance earlier we said was 2 squared, which is now 4. And we're going to divide that by the sample size, 25. Yes, I thought 25. And we want to look at the probability that me getting a mean average of 11 meters. Yeah, what is that probability really? Is it going to be in this 1%? Is it going to be in this region here, the acceptance region? We just don't know. Let's find out. So we say the probability that X bar is greater than 11. Now you see, I could put greater than or equal to here, but it makes no difference in this case because it's a continuous distribution. So first thing, really, with any normal distribution problem, you've got to remember to standardize that. So we can change this to the probability that Z is greater than So we take my value here, 11, and then we take away the mean, which we think is about 10, and we put it over the standard deviation, which, as the variance is the standard deviation squared, and this variance right here, we're going to have to square root this bad boy. So it's the square root of 4 over 25. That's actually quite nice. Actually, you can square root the top, square root the bottom. That's just going to be 2 over 5. Quite a nice number there. If we simplify this down a bit more then, because we want a real number in decimal form so that we can look it up in the tables later on. So, let me just do this in my head. It's about 2.5, yes, there we are. So we're looking at the probability that Z, which is the normal distribution, if you will, is greater than 2.5. So click over to your tables now. We can look at the normal distribution page, and if we look down this page to find out the probability that Z is being less than 5, remember these are cumulative, so you can only look up the less than probabilities. So what we'll have to first do is change that to 1 minus the probability that Z is less than 2.5. See where we're going with this? And basically, work out that from the tables. So the probability that Z is less than 2.5 is 0.9938. So 1 minus 0.9938. 1 minus 0.9938 is, of course, 0.0062, which equates to, just move over here for space-wise, 0.62%. So if there's a 0.62% chance of me getting this 11 meters, it must be somewhere in this critical region here. So, the conclusion of this test, we can say that there's been significant evidence to suggest that the mean is not 10 meters, new scientists. It's actually greater than that, hence proved by Stephen Rose with my snake catching ability. Thank you very much. We're now going to go back to Paul in the studio. I hear he has some fascinating news for us. This has been Stephen Rose, signing off.
Thanks, Steve.
For the final part of today's show, we have a guest appearance teaching us an exam-style question. Now, some say he was born with a snappy dress sense. Others say he acquired it over time. All I know is he's damn good at equations. Let's hand over now to Professor Paul Carter.
Boy, Steve, this calculator is the bee's knees.
That it is, Paul. That it is.
Thanks, Steve. Okay, so I've got a good example for you today. We have a machine and it's producing rods at 2 centimeters long with a standard deviation of 0.02 centimeters. We're going to take 10 for example, and we're going to see on the 5% hypothesis test whether it's correct or not. Alright, so as taken on 10, we had this length of 2.04, 1.97, 1.99, 2.03, 2.04, 2.10, 2.01, 1.98, 1.97, and 2.02. Now my first job that I've got to do is I've got to find the sample mean. So to find the sample mean, I'm just going to take the mean of those. So I'm going to add them all up, divide them by 10. And our sample mean today is going to come out at 2.015. That can be our sample mean. So, what is our hypothesis test? Well, our hypothesis test is to test whether the length of 2 centimeters is good. So, and 2, that's going to be is not equal to 2. Okay. So our population mean is distributed normally, as it is. So our mean is distributed normally with a mean of 2, as we saw, and distribution variance. Yeah. So the standard deviation squared divided by the total number for the variance of the group. Yeah. So what we're trying to do is we're going to try and see whether when p is greater than, when x bar is greater than or equal to 2.015, which is our sample mean, whether we're going to get something within 5% range. So what we're going to do first is the center value. So z, 2.015. We take away our 2, and then we're going to divide by our 0.02 over root 10. Which comes out p z is greater than 2.372. Yeah, and then we can write this because it's a greater than or equal to. You can write this as 1 minus 2.372. Now, if you go to your normal distribution tables, thank you. Yeah, you know, you can see what you can see what that's coming out of. So it's going to be 1 minus our 0.9912, and that's going to come out at 0.0088, which is equal to 0.88%. Because we're testing on a two-tailed test, it's got to be within 2.5% here and here. Yes, just get this over here. Since the 0.88 is less than 2%, the result is significant at 5%, and it can be assumed that the mean length has changed for the rod being created. So, because this is less than 2.5%, means it's a significant change in the length of the rods. Thank you. Back to you, Steve.
Thanks, Paul. I'm afraid that's all we've got time for tonight, folks. I hope you've enjoyed this special edition of S.T.A.T.S. News. Stay classy, stats class.
S.T.A.T.S. News in no way endorses Casio or their affiliates. We aim to provide unbiased news wherever possible. S.T.A.T.S. News does not accept any responsibility for damage that has occurred directly or indirectly. If you are suffering from headaches, nausea, memory loss, or a sexually transmitted infection as a result of this show, please feel free to keep your complaints to yourself.
But wait, we're not done yet, folks. Now it's time for some recording fails.
So, thanks, Steve. That was mind-blowing. Right. Thanks, Steve. That was mind-blowing. Now we're going to go over to my identical twin. As I'm understanding it, how is that?
Hello there, children. I'd like to take a minute to talk to you about the fabulous world of statistical hypothesis testing. Oh, excuse me. I was just going through some theories before we started this video. Let me just clear those off for you. Okay, so you might be sat there wondering, what is a statistical hypothesis? Well, first of all, let's learn how to spell it. H-Y-O-P-O-T-H-I-S, like that, I'm pretty sure. Okay, so a statistical hypothesis is basically where we make an assumption for a parameter that we don't know. it wrong?
Does it get HYP?
Damn it, I was
Start
doing
again?
so well.
Start again? I'm sure that's how it's spelled. Really? Thanks, Steve. That was mind-blowing. And now we're going to go over to my identical twin, who, as I understand it, is outside getting us some views on hypothesis testing at the moment. That was crap. Right, let me do it again.
Okay, let's keep going.
Thanks, Steve. That was mind-blowing. Now, let's go over to my identical twin, as he...
Welcome to the University of Scunthorpe, the worst university in the UK. Here we teach you how to do very good degrees, like the philosophy of Harry Potter and no.
Thanks, Steve.
And can we start again? I was adjusting my glasses.
I apologise. Thanks, Steve.
For the final part of today, I said final.
Final.
Okay, let's start again quickly.
Thanks, Steve.
For the final part of today's show, we're going to be... we have a guest appearance. Okay. Okay, tell me when you're ready.
Yeah.
I'm afraid that's all we've got time for.
Yeah,
tonight,
there we
folks.
go.
That's the only thing you say.
Yeah.
Wait, okay.
Should I say something? No.
No, because we're taking the audio out of this. We'll
Have
probably
you
have the music in the
Have you got
background.
any ammunition, sir?